Hello and welcome to episode 24 of CS350 Online. I'm your host as always, Leslie Eisted. Now, today's episode, for those of you who decide to tune in, is not an official episode. That means that anything covered today you are not expected to study for the final assessment. But you might find it interesting. Now, normally, this is where we would cut to an OS of the day, and I would tell you all about what's going on today. Well, I will tell you about what's going on today. So today we're going to talk about how to design an operating system and look at just some of the different design considerations you might take when you are building one and how that might impact different parts of the operating system. And then we're going to take a look at a specific operating system and its design decisions and discuss how those design decisions have impacted that particular operating system and the user programs that run on it. And because we're going to talk about an operating system later, we're going to skip the OS of the day for now. So one thing before we get into just talking about the design of an operating system, in our last episode we talked about networking, and I just wanted to review the fact that what we talked about in episode 23 was a really high level discussion of the networking layers and how they integrate with the kernel. And I probably made it seem like this has to be the way that networking sockets integrate with the kernel. And like anything with computers, that there's more than one way to do it. So that was just a theoretical high-level discussion of how you could do it. That doesn't mean operating systems specifically do it that way. Now, for some of the discussion, I was using the Linux kernel documentation as kind of a reference, but again, every OS is going to do something a little bit different. And in fact, many operating systems, especially those which are considered microkernel, may not include very much networking actually in the kernel itself. As many of you know, even some microkernel operating systems, they don't even include virtual memory in the kernel. All right, so then let's talk about designing an operating system. So there's a lot of work that has to go into designing your own operating system. And there's a lot of questions before you can even sit down to start to write the code, before you even come up with a name for your OS. There's a lot of things that you need to take into consideration. And this isn't just true of an operating system. This is true of any major project that you're undertaking. So whether it's you're trying to do your final project for computer graphics whenever you decide to take it, if you decide to take it, or maybe it's your final project for some other course or side projects, there are lots of very high-level design decisions you need to consider before you can dive in. And for an operating system, one of the biggest things you have to ask is, what kind of programs are you trying to run? So what is the purpose of this operating system? What is it going to run on? What kind of hardware? Because how you design an operating system for something like the computer sitting in front of you is going to be vastly different for designing an operating system for a POS device, which I know probably sounds like a piece of shit device, but no, what I actually mean is the point of sale, little receipt printers. A receipt printer may need some networking in order to, send Wi-Fi signals, but it's not going to need things like pipes. It's probably not going to need a terribly complicated graphical UI. There's a lot of design decisions. So knowing what kind of hardware you're going to run on is actually a big part of this. And also knowing what kinds of programs you're expecting the operating system to be executing is also very important, because obviously your desktop computer, you're going to be anticipating that you're running things like Chrome and Firefox. And presumably you want to be able to run video games. And that is a very different kind of environment from building an operating system for a robot that only ever runs very simple programs that simply dictate the robot's motions. So you need to know what kinds of programs are you going to run, and for what kind of hardware are you going to be designing this OS to run on. You also have to ask yourself, who are your users? So who are the people that are going to be using this operating system? Now that may not make a lot of sense, but it actually does make a lot of sense. Because if you're designing an operating system for, let's say, people in CS at our school. There's a lot of concessions that you can probably make about usability because we are very technical people. And if you give us a shell, most of us are probably pretty happy. But if you were to say, try to design an operating system for a child, like a 5-year-old, most 5-year-olds can't type because their hands aren't large enough to actually sit on the home row. Sorry, context. I tried to get my 5-year-old daughter to learn to type. Her hands aren't quite big enough to do it yet. So you have to ask, who are your users? Are they super technical people? Are they not technical people? Or are you anticipating a blend of people? And not just who are your users, but you need to ask how many users. Because if you're designing an operating system that's only going to run for one user ever, then there's, again, a lot of concessions that you can make. Whereas if you're designing an operating system that could be used by multiple users at the same time, then you have to take that into consideration. Then you have to ask questions, does security matter? Because maybe if this is an operating system that's designed for 5-year-olds, and there's only one 5-year-old using it at a time, then maybe security doesn't matter. Because, I don't want to say there's no 5-year-olds out there who can't hack the system, but the majority of 5-year-olds I know certainly can't hack the system. So you have to ask yourself these questions so you can figure out, do you need to integrate security? What kind of security should you be integrating into your operating system? Then you have to ask questions like about performance. Does it matter? Now, most people are going to say, well, performance always matter. But how does it matter? Does it matter that I must guarantee a response to an event within, 10 milliseconds? Or can I let it go 20 milliseconds and the user will be perfectly happy? Is this an operating system that's being designed as a real-time OS for controlling vehicles? And so our response times really matter. So our performance in general really matters because we don't want to run over people. Or is this just like another Windows clone and it doesn't matter if we take an extra 10 milliseconds? And then there's questions like, do you want to attach it to a network? Do you want to have a graphical interface? There's lots of very, very high-level questions you need to ask before you even start to dive in to the individual components, like which kind of virtual memory do you need? One of the ways that you can kind of think about this is, let's suppose you are Amazon, and Amazon, if I'm sure many of you know, they have these Amazon Web Services. They have this platform where you can rent time on their farms, which they've actually built more farms so that you can actually rent time on a farm that's nearest you. Sorry, I'm calling it farm. They call them data centers. I call it farm because render farm. It's not a render farm. Now, if you were Amazon and you were trying to develop some brand new operating system to run on your data centers, the considerations that you'll have to make are pretty immense, because you're not talking about 5 or 10 users. You're going to have to do an analysis and figure out how many users exactly are you anticipating could be on this machine or that using this data center at any specific time. And security is going to really matter to you. And then you're going to have to you may even have to consider things like, how do I reduce my power? Because if you consume a lot of power, you're going to generate a lot of heat, which is going to cost you more money to cool down. So there's all kinds of different considerations that Amazon would have to make an OS for their data center. They can't even talk about implementation until they figure out exactly what problems are they trying to solve. What is the market that they are trying to address? So one of the first things is architecture. What architecture is your operating system actually going to run on? Now, OS 161 runs on a MIPS R3000. It doesn't really run on anything else. And there are many operating systems, by the way, that only support a single architecture. And then we have to ask, well, do we want it to support just a single architecture, or do we want the operating system to be fairly portable in that we can actually easily move it from one architecture to another? And there are different ways that you can actually implement portability. Portability could be something like it's very easy to recompile for a different architecture. Or you could simply offer, there's lots of ways you can implement purpose. Making it easy to just change a flag for your compiler that says, okay, make it for MIPS or make it for ARM. That's going to be one of the easiest ways to do it. And essentially, in order to implement that portability, what you're looking at is there are some very specific files of the OS where you'll have to have multiple versions, and we'll look at that in a minute. So if you are going to support a single architecture, it's actually quite easy to implement your operating system because your implementation will be simpler to maintain and it will be simpler to code, because when you're implementing something like a spin lock, you only need to make one implementation. If we were supporting multiple architectures, we'd actually have to maybe implement several versions of a spin lock, one for each specific architecture, or at least we would have to make use of preprocessor directives to make sure that when we're doing inline assembly, if arch type equals R3000, then here's the assembly to do the atomic test and set. And if arch type equals X86, then here is the assembly to do the atomic test and set, and so on and so forth. And if you've ever used any or looked at any like Linux code, you actually see a lot of these preprocessor directives that are specific to the arch type. And some of these files are actually crazy. Like there'll be one for PowerPC, which is what Mac used to be. There'll be ones for Spark. There'll be ones for 32-bit x86 processors. There'll be ones for 64-bit. There'll be ones for AMD architecture. So there'll be just dozens of these different arch types. And it's to make the code so that it doesn't matter what architecture you're running on, you can just change a compile time flag and we will be able to build the code for that. And if you're only supporting a single architecture, you won't have any of that nonsense and you'll have a singular implementation, which of course makes the implementation simpler and easier to maintain. Of course, the downsides of supporting only a single architecture is that you live and die by that architecture. So you have a questionable longevity. I mean, presumably if you're going out to make your own operating system, you are either one of these individuals who just wants to bring goodness into the world. And here's my new free OS, isn't it awesome? In which case, great. And who cares about the longevity of it, really? But if you are a company and you're designing an operating system, you don't want the OS to have a fixed end of life. You don't want to know that in 3 years, when that architecture is no longer supported by anyone and no longer being manufactured, you don't want to know that's the end of your OS. So there are longevity issues with single implementation ones. Or at least there can be. And then, as I mentioned, it's not, if you do decide to go with the singular architecture, there are some other interesting consequences. So the code's going to be simpler because you're not going to have so many preprocessor directives, which makes it easier to maintain. It actually makes the code really easily readable and understandable. And if you're looking at OS 161, which is kind of based on a BSD-like model, it's actually very easy to understand the OS because at no point do you have to understand multiple architectures. You know that this OS was designed and runs on the R3000, not the R4000, not the R2000, the R3000. So as long as you have a basic understanding of that chip, or at least some of the features of it, then diving deep into the assembly code is easy even. But one of the other side effects is that when you support only a single architecture, you're going to have fewer external devices to consider because this is really architecture dependent, but you can imagine that an x86, like let's talk about a 486 or a 386, which is roughly, I think, around the time of the R3000. I'm not sure. I don't remember when I had a 486. I mean, I remember when I had a 486, and I think it overlaps with the R3000, but I don't quite remember. So if you were to compare, however, the number of devices that are a 486 computer had, Intel 486, and compare that to the number of devices that would be available for the MIPS R3000, there's a big difference between those two. The MIPS R3000 is an architecture that is used for things like PlayStation 1s. How many devices are supported by the PlayStation 1? Not many. And so the OS there doesn't have a lot of devices to actually consider. So in many cases, when you are supporting a single architecture, your operating system, because it is in a restricted scope, doesn't have to support as many crazy, wild devices. It's not to say you don't have to support a lot. It's just to say there are many cases where you don't have a lot of devices to choose from. Now, if you are supporting multiple architectures, the implementation is going to be a lot more complex because things like spin locks are going to be arch specific. So that little atomic test and set block, you're going to have like however many different architectures you support, you're going to have one block for each of those. And that's going to make the code really hard to read. But it's not just spin locks, things like the exception handler. So if you remember common exception, which is the little bit of code in OS 161, which runs when you are when the CPU receives an exception. Well, you're going to have a different version of that common exception file for every single architecture, because each arch is going to be supporting exceptions possibly in a very different way. For example, suppose I want to make an OS that supports both x86 and the MIPS R3000. Well, in an R3000, we treat exceptions and interrupts as exceptions. So we don't have to differentiate between the two. We only need one piece of trap code, whereas another architecture like an x86 may differentiate between exceptions and interrupts. And so you actually need multiple separate exception handlers. You may need an explicit exception handler and an explicit interrupt handler to be put into the trap table of the arch. So when you support multiple architectures, any of the lower level code bits, the assembly bits, anything that's architecture specific, generally the assembly bits or the inline assembly in your C code, you're going to need to have multiple copies of that. And that's going to make, as I said, your code harder to read. It's going to bloat your code up and have all kinds of interesting consequences. But of course, that's actually what most operating systems are today. So Linux, of course, supports multiple architectures, Windows to a lesser degree, but you get the point. So then you really have to ask yourself, and this is before we dive into specific implementations of things, what is your kernel going to abstract? So believe it or not, there are some operating systems out there that don't really abstract anything. So for example, that means that they don't use virtual memory. The addresses that processes use are the actual real physical addresses. And I mean, this isn't actually a new concept because older versions of DOS, they didn't use virtual memory. They used the physical addresses. And everything ran in privilege mode. So you have to consider, are you going to abstract anything? And if you're going to abstract things, what are you going to abstract? Are you going to abstract devices? Are you abstracting networks into sockets? Are you going to abstract how data is stored into a disk on a file system? Or are you going to let the users just directly write bits to the disk themselves? Are you going to abstract the execution of programs into processes? Which of those design abstractions are you actually going to do? And what are the consequences if you don't do this? So for example, from a security perspective, if I don't abstract physical memory, then, my user programs wouldn't actually, they would actually be able to access other address spaces. But there's actually another interesting consequence that we'll see a little later of actually letting the user programs use physical addresses. Most architectures have an MMU, and the MMU is almost enforcing that there is virtual memory being used, but you can actually bypass it in a sense by simply having the relocation and limit registers or the page tables just do an identity mapping. So the hardware still believes it's doing the abstraction, but the OS itself is just doing an identity. And there's interesting consequences of that for the implementation, but there's also interesting consequences of that for user programs being able to talk to each other directly. And then some other things that you might not have thought about. So, and I mean, it's not here, but do you want this operating system to be real time, or do you want it to be more like a consumer desktop operating system? And that's going to make some pretty big decisions for you. I guess that's on the next slide. Here, we'll go there. So do you want a real-time operating system? So if you want a real-time operating system, then you're going to have to take a little bit of extra care and extra time to figure out, okay, what kinds of guarantees am I going to offer to the user programs, and in terms of response times and so on, in terms of sharing of the CPU, and how am I going to facilitate those guarantees? How am I going to make sure that those guarantees are actually being met by my kernel? And if you're not doing real time, you still have to discuss things like, how am I going to guarantee that responses actually happen in a reasonable amount of time? And part of this, of course, would be choosing appropriate scheduling quantums. So if you're going to design an operating system, you've got to decide real time or not real time. And then there's the discussion of monolithic or microkernel, because you could put everything in the kitchen sink in the kernel if you wanted to, which gives you, I feel, a greater control over the system as a whole, greater control over device behaviors. Everything is tightly linked together. Probably easier to implement a monolithic kernel, because the device drivers are in the kernel, and since everything's in the kernel, then they all integrate very seamlessly together. But one of the problems of creating a monolithic kernel is you end up with a really, really large code base, which makes it really hard to debug. For example, if you look at Linux is millions and millions and millions of lines of code. Massive code base. And most of the code for Linux is actually device drivers. Same is true for Windows, actually, which is also a monolithic kernel. But what's interesting is, because the code base is so large, debugging issues like deadlocks and race conditions are really, really hard. And Google actually had this tool to analyze code to look for race conditions and deadlocks, and they found over 300 in Linux alone that are unsolved, that are still there, sitting in the code. And Linux is obviously not going to be the only one that suffers from this. I promise you, every major operating system suffers from this. And of course, if you have a microkernel operating system where you put the minimum into the kernel, you'll have a smaller code base. It'll be easier to debug. But now you have a lot of aspects of the operating system which are living as user programs, which gives, and I mean, sometimes operating systems do this so that the user can plug and play different components. But then you would be giving potentially away some of the control over the system's implementation, which may make code buggy. So there are lots of decisions to make there. The other thing is, you want to go micro. Why would you go micro if it's harder to implement? Because it is hard to implement. Why would you go micro? Because you want to put it on a device. So you want an embedded operating system on a device. So QNX, for example, often embedded. There are very interesting sounds coming from my basement. I have no idea what they are. All right. So then let's talk kind of about multiprocessing here for a minute. So do you want to, in your operating system, support multiprocessing or threading? Do you want the user to only be able to run one program with one thread? And I mean, the very first operating system I used, that's all it supported. One program with one thread. There was no concurrency supported whatsoever. And at the time, and you might be thinking, why would any OS make that decision in the 80s or 90s? Well, at that time, if I was playing a game, I didn't need to be on WordPerfect and the internet at the same time. I didn't even know what the internet was in the 80s, because it wasn't the same as what it is today, obviously. So this is why knowing who your users are and how many users you're going to have and what kind of programs you want to be able to execute, that's why it's important to know that in advance, because that's going to impact your decision on how do you support multi-processing and multi-threading, or do you support it at all. And let's suppose that you do want to support both of these features. Now you have to make some other design decisions too. And this should be fairly familiar for you, because if you look at how you implemented A2A and A2B, you had some freedoms at implementing part of the processes in the kernel. So for things like, what's the maximum number of supported processes? Are you going to have a fixed number? And this is even actually tied to how you implement memory. Because if you choose to do something like dynamic relocation for your virtual memory, that is going to enforce a maximum number of supported processes. So these things are very much connected together, which is why you need to make these decisions before you sit down and actually start writing code. Then you have to talk about, okay, so let's suppose I want to support a maximum of maybe 100,000 processes. That seems very reasonable to me. I don't think I've ever gotten close to that, except when I read Fortbomb. And then you ask questions, do I want to be able to reuse my PIDs? And being able to reuse your PIDs is related to the discussion of how do people use your operating system. How long can you anticipate your OS is running for before it's rebooted? If you are writing an OS for a data center where you've got lots of users coming in and leaving, then you're going to end up needing to support large numbers of processes, but furthermore, you're going to want to be able to reuse those PIDs, because you're going to run out very quickly before the OS actually gets restarted. So a long-running OS with lots of users coming and going is going to definitely want reusable PIDs. But if you're not anticipating a lot of users or a lot of processes coming through, then maybe before there's a reboot, then maybe reusing PIDs isn't as important to you. For example, if you've got a smartwatch, and I have not an Apple one, I've got a Sunto one up there, just measures your heart rate and stuff. That watch's operating system does not need to support processes. But if it did support processes, it doesn't need to support reusable PIDs, because there's no way I would run that many processes before I ran out of PIDs. So you have to think about this. And then you have to ask yourself, so how many process management calls am I going to support? Am I going to if this comes into the discussion of, am I abstracting the user program from the kernel or not? What level of security am I offering? If I offer no security, then I don't need to offer system calls. I can just have the user programs directly interact with the kernel to call fork. But if I do abstract the user programs from the kernel, then I'm going to need to support system calls. Which system calls would I support? And in particular, things like fork, what's the behavior of fork, what's the behavior of exit? Those are fairly standard things, but things like the synchronization between processes, that's where operating systems, I feel, take some pretty big differences. So OS 161 only supported wait PID, which is wait for your parent to die. But if you look at Linux, Linux actually supports a number of different synchronization for processes, which is kind of neat. But those can actually be quite difficult to implement. So you've got to ask yourself, again, what kind of behavior are you expecting from your user to know which kinds of system calls do you need for your processes? And then you need to ask, do your processes, should they be able to have multiple threads? OS 161 does not permit user processes to actually have multiple threads. So we don't have a user level threading library. We don't have system calls to create, destroy, or yield threads. So if we don't want to support that, then leave it as OS 161 is. But if you did want to support multiple threads at a user level, then you're going to have to add system calls and kernel implementations. And then the other things that you have to think about with processes is, do you want to support inter-process communication? And how do you want to support that? Now, IPC can kind of be trivially done with without involving, specialized things in the kernel. So you can actually use a file. So if you create a file in one process and start writing to it in that process, then another process can also open that file and start reading from the file. So there are ways of doing IPC without building it into the kernel, but synchronization becomes a real nightmare. So you might want to have the kernel actually have system calls to do maybe a message passing system call to go send data between processes. Something that shows up in Windows and in Linux sometimes is shared memory spaces. So you can actually create a region of the address space that both processes can see. So they can read and write to it at the same time. Or you might just say, you know what, screw these traditional IPC methods. If you want two processes to talk to each other, you got to use networking. I mean, that's probably what I would use. But decisions. Once you've thought or as you were thinking about processes and threading, you also have to think about scheduling. Because if you're supporting multiple processes, then you're going to want to be able to schedule them. Do you want to give your users the illusion that all of these things are running simultaneously, even if your hardware doesn't support that? And if you are giving them that illusion, then you need to ask yourself, am I supporting time sharing? Am I going to just do things like a cooperative concurrency where I don't preempt threads. I only permit context switches when a thread blocks, exits, or yields voluntarily. And that comes into play with both the design of your process and threads library, but also comes into play with implementing context switches and scheduling as well. And when you're talking about scheduling, you'll have to ask, okay, how do I select if I'm doing preemptive concurrency, then I need to select an appropriate scheduling quantum. And what should that be? And then knowing what your scheduling quantum should be depends on what kind of scheduling algorithm you're going to use, because things like the lottery scheduler and completely fair scheduler and round robin, they have a uniform, so the scheduling quantum is the same for every thread, but MLFQ has different scheduling quantums based on priorities. So all of these things, again, are very much tied together. I never said creating an operating system from scratch was easy. And then you have to talk, of course, about virtual memory. So, are you going to use it or not? Now, as I said a little bit earlier, most architectures have an MMU. And if the architecture has an MMU, then it's probably going to pass every address through it. So you may have to implement virtual memory, whether you want to have it produce the identity or not. That is your decision. But if you are going to use physical addresses, then you need to be aware of the consequences of using a physical address. There are consequences. And then let's suppose you're not going to use physical addresses. Let's suppose that you are going to use virtual memory for both the kernel and the user program. You've got to ask yourself, how am I going to differentiate between the kernel's addresses and the user's addresses? So how am I going to solve the sharing problem, and how am I going to solve the bootstrapping problem? Which, if you remember, the bootstrapping problem is how do you have the kernel, which implements and manages virtual memory, boot using virtual memory? So we usually solve that that is solved specific to the architecture. And then the sharing problem, we usually do that thing where we subdivide the address space into two distinct regions where you've got, these are the kernel addresses and these are the user addresses. And what do you want the split to be? Now, we always talk about a 50-50 split because that's, what most OSs that we use do. But, if the majority of your programs are going to spend the majority of their time in the kernel and the programs themselves don't use a lot of memory, then it doesn't necessarily make sense to do a 50-50 split. Maybe you'll do a 25-75 split or a 1/3, 2/3 split and dedicate more regions of the address space to the kernel than to the user program. That's why it's important you know what kind of programs you're going to run, because even simple decisions like how do I divide up the address space, we need to know. What programs are you running? If I'm running stuff like MATLAB, which is a very large, beefy user program, I'm probably going to want to do a 50-50 split. And then we have to ask questions about how do we load the address spaces themselves into memory. We talked about two main strategies, and there are consequences to each of them. So address space preloading, which is what OS 161 does, what it's going to do is when you load a user program, OS 161 is going to allocate and load the entire address space of the program into physical memory immediately. And there are good things that happen. It means that the entire program is in memory, and so once you've loaded the program, at no point do you need to go to disk to get the next instruction to execute. So it's going to be faster runtime execution because we don't have the concept of page faults. Of course, the problem is that if you're loading the entire address space and the address spaces are huge, you're going to be restricting the number of processes you can run at the same time. So you've got to ask yourself, how many users? What kinds of programs are they running? Because that's going to help you decide whether address space preloading is appropriate or whether you need to do on-demand paging. Now, to recall this on-demand paging, that's where we only load the portion of the address space we need at the point that we actually need it, which means that our address space lives on secondary storage, which is much slower. So we need to, implement cache algorithms to support that and so on and so forth. The downside is that performance-wise, on-demand paging is slower than preloaded address spaces. But the upside of on-demand paging is we can support more users and we can support more processes. So on-demand pages is what most operating systems are actually using. And then you're going to have to decide which particular implementation of virtual memory are you going to use. This is somewhat tied to your architecture, of course, because your MMU is only going to support very specific things. For example, OS 161 or our SYS 161 or R3000 has a paged MMU. However, there are ways of shoving things like segmentation down the throat of a paged MMU, as you see in OS 161. And that's simply, instead of implementing true page tables, when we're allocating the code segment, instead of just grabbing 7 random pages, we just grab 7 contiguous pages. And that is effectively segmentation on a paged MMU. So you've got to look at, what does your architecture support? You've got to look at things like how much memory is actually going to be available, because if you are trying to support an operating system on a system with low memory, let's say my first computer only had 256 kilobytes of RAM, which at the time I thought was awesome. The 256 kilobyte of RAM was this big. It was this giant board that actually didn't fit entirely into the computer. So it was actually designed to hang out the back a little bit, which probably sounds very bizarre, but there you go. My second computer had 30 megs of RAM. Those, obviously, how we're going to implement things like virtual memory for those kinds of systems is going to be very different from how we implement virtual memory for something like the computer sitting in front of you. So my MacBook here has 32 gigs of RAM. So I can actually do a lot more with this. I have a lot more options available to me than I would otherwise. And then you have to ask yourself things, again, it comes down to users. And how many process do you anticipate? Because if I anticipate that there's only ever going to be one user and one process, then I probably, if my MMU supports it, I'm just going to use dynamic relocation because it's fast. I'll give my user the best experience they could possibly have. And I don't have to worry about fragmentation because there's only ever one process. But if you have multiple processes, then fragmentation starts to become an issue. Interesting problems, right? You also, there's other things to discuss here in the topic of virtual memory. How many bits do you use for the virtual address? Well, in order to know how many bits you use for the virtual address, you need to have an understanding of the architecture. How many bits does the MMU want to use for the virtual address there? Maybe you want to use fewer. That's actually possible because what you're just going to do is make the higher bits all zeros. Maybe, but if you're going to use fewer bits than the architecture supports, you would only do that because you know that the address spaces of the programs that the users are going to run are very, very tiny, which is why you need to know who are your users. What are they running? All right. You also have to ask yourself about what devices you're going to support. And this is actually a tricky discussion. So it's not just about what devices do you want to support right now. You have to think to yourself, what devices do I want to support in the future? And how do I want to support devices? So this is the question of how easy should installing a device be? Today, devices are plug and play. Most of the time when you plug a new device in, and when it powers on, it may fire an interrupt to notify the CPU that it exists and what it is, and that interrupt will get handled by the kernel of the operating system, and the kernel will be like, oh, I see you just plugged in a Wacom Intuos tablet. Okay, I know what that is, and I have the driver built in. So you plugged it in, and it just worked, and you didn't even have to think about it. That is an interesting feature, but it's also quite difficult to implement. Because in order for that to work, you've got to be able to recognize interrupts from devices that you don't currently have running, and you also have to have a massive database built into the kernel, probably, that knows about a whole pile of common devices to anticipate. So plug and play is actually one thing that you need to consider. Or you could do something where you just require the manual installation of all drivers. I feel like my first computer that ran the internet, this was more of the approach it took. It was supposed to have some kind of plug and play ability, but it was like Windows 3.1. So it didn't really work. And it was a nightmare. So this comes down to your users. If you can't anticipate your users are capable of dealing with device driver issues, then you don't want to offer them only manual installation of drivers. You want to offer them plug and play. But if your users are a little bit more tech savvy, then it's probably okay for some devices to have to manually install the drivers. Something to consider. So this actually kind of comes into the job of what devices do you support today and what devices will you support tomorrow. You're asking, how easy will it be to add new device drivers in the future for tech that we haven't seen yet? And for tech that exists today, how easy is it going to be to install and use those devices? Now, the other thing that a lot of people do is, what legacy devices do you support? So if you were to look at something like the Windows kernel, which I've never seen the code, I've never worked at Microsoft. But Linux, if you look at the Linux kernel, as I said, the vast majority of it is actually in things like device drivers. And there are devices that are supported which really make you scratch your head, because I have not seen or heard of this device in over 25 years. And a lot of people might be thinking, well then, why should I support these legacy devices? Like, why would I support a 16-bit Sound Blaster card from the early 90s? Why would I support that? Why would I support an NVIDIA Riva TNT2 graphics card, which is from like the late 90s? Why would I support that? That card nobody uses anymore. And yet, what you find is in many operating systems, those devices are still actually supported. So the first question is, why do most operating systems like Windows and Linux support legacy devices? Just because you are using a nice modern piece of technology doesn't mean that all of your customers are using nice modern technology. If you look at some major banking institutions and just bigger companies in the financial district, you'll see that they have a tendency to not let go. I remember when I was in high school, and if you're the tech person in town, or they want you to come and fix their computer. And my mom was working part-time at the bank, and she must have told her coworkers that I could fix computers. And so they asked me to come in and take a look at their computer. And I go into the bank, and I go into the basement, and I met with a mainframe. And it's the mid-90s. It was actually the mid to late 90s. And I'm sitting there, and I'm like, I don't even know what this is. I mean, it was really cool, but I didn't at the time even know what it was. I had never seen a mainframe in person. So there are lots of places that really hold on to technology. And there are reasons why they do it, because they've invested a lot of money both in the hardware, but also in the support for the hardware. And they've got themselves to a point where even if it's not perfect, they understand how it works right now. And if it breaks, they know the way that it's going to break, and they know how to fix those problems. And what it does overall is minimize downtime, which in a lot of ways minimizes costs. And so a lot of places have a tendency not to upgrade because they are afraid that if they upgrade the hardware or if they upgrade the operating system, that it's going to push them into a place where they don't know what's going to happen. They don't know how to handle the new errors. They don't know how to handle the new breakdowns. So it's going to cost them time, and it's going to cost them more money to solve those problems. And so a lot of companies, as a result, don't upgrade a lot of back-end machines very often. And as a result, if you want your operating system to still run on these companies' hardware, you need to make sure that even if you are supporting all of the new stuff, you still have to support all of the old stuff. Now, Apple, interesting story. Apple has actually, I feel like they have recently started to drop a lot of support for things. And this actually bit me in the ass real hard a few months ago. So I work with stereo 3D images, and there is a program called Stereo Photo Maker, which is a free program. And it is, I've been using it for years. What it's used for is, creating 3D images, exporting them to different formats, adjusting them a little bit, rectification, turning them into anaglyphs and so on. And I use this for my research. This tool is essential for my research. What I didn't know was that this application was 32-bit. And I didn't also know that when you upgraded to Catalina, that Apple had dropped support for 32-bit applications. So when I upgraded to Catalina, Stereo Photo Maker stopped working. I understand why they made that decision, because most users in their pool aren't using 32-bit applications. But there are a few of us that are using obscure or legacy things that they just broke everything for. So it's a good example of why people support legacy, is because you never know who you're going to make angry. Another thing that you have to take into consideration is how do you communicate with the device registers? So your hardware probably is going to support certain kinds of things. So you may have DMA, you may not have DMA, you may have memory mapped I/O, you may not have memory mapped I/O, you may only have port mapped I/O. And so you're going to have to tie how you implement device drivers into what your architecture actually supports as well. And again, this is why when you're trying to make portable operating systems that can be recompiled for other architectures, the code gets really hairy, because you're going to have architecture-specific implementations of a whole pile of different things. That's actually why abstraction is really important. Comment on Twitch here about how there's still lots of pages of Fortran jobs. I believe it. One of my co-op jobs was Fortran. Yes, I am a Fortran programmer. And in fact, even during co-op, I interviewed for a lot of Fortran positions. So who uses Fortran, just as an example of legacy things. So I was using Fortran at the Canadian Ice Service, which is part of Environment Canada. They were using Fortran to do iceberg tracking. And I mean, Fortran is actually a really cool language. One of the interesting features of it is that most lines of Fortran can translate into a single assembly instruction, which makes it really cool. I mean, not the modern Fortran so much, because they've added stuff like structures and stuff, but if you're looking at stuff like Fortran 77 and before, yeah, it's pretty cool. So it's actually a really fast language because you get a really small assembly program. But we weren't actually using Fortran because the Canadian government wanted to use Fortran. We were told that we were using Fortran because some of the customers and some of the other countries that were using the iceberg tracking software required the programs to be written in Fortran. Another place where Fortran is still used, and again, just as an example of legacy stuff, is stuff like the space programs are still using a lot of Fortran. So satellites, a lot of that is still done in Fortran. Yeah. If you're really bored in the next month, learn Fortran. It's kind of fun, actually. And you might put yourself into a position where you can get a job, because not many people know Fortran these days. And if you really want a job, learn COBOL. It's one of the only languages I have not, like legacy languages, I haven't had a chance to take a peek at. But there are so many companies out there that are still using COBOL, and the problem is all of their COBOL programmers are retirement age. So they need to find young people to replace them with, except nobody these days has really even heard of COBOL. So learn COBOL. It'll be fun too. You can tell all your friends. And you'll be like the coolest person ever. All right, other things that you have to consider are stuff like file systems. So, what kinds of file systems are you going to support? Are you going to support just a physical file system? Are you going to provide a virtual file system? Are you going to support attaching multiple different file systems? How do you present that to the user? Are you going to use mount points? Are you going to use two-part namings? Are you going to do something else? And what is in your logical file system? What kinds of API and high-level instructions are you going to provide to your user programs to use? Or are you going to require that every user program does all of their own I/O stuff themselves? I mean, back in the 50s, that's what they did, right? And then if you're going to make your own file systems, which many operating systems actually do this, how do you implement this? Are you using inodes? Are you using something like blockchains? That's chaining. And if you do something like inodes, are you going to implement caches in the kernel? So a lot of operating systems, because they are aware that accessing secondary storage is actually very, very slow, they will make sure that the kernel is implementing inode and data block caches so that we can actually get things from memory instead of going to secondary storage. And if you're doing that, how are you implementing that? How much memory will you set aside for that, which depends on the architecture you're using? Or are you going to utilize special devices to handle these block caches? So if you have an Intel Optane, which is persistent RAM, then how you would implement a block cache would be very different if you had in the presence of an Optane, because you would actually be doing it through a device instead of doing it through regular memory. Lots of decisions. And then, of course, there's networking. So, I talked about some of the design decisions with networking and some of the ways that it does work. But what are you going to support networking? If you're supporting networking, are you doing it through system calls? Are you going to just present a bunch of libraries at the user level? Are you just going to give the user sockets, a TCP and a UDP socket, and say, go, this is what you get? And then you have to ask, okay, what is the OS going to implement as part of the networking? Is it going to offer us, that's some good spelling, a DNS cache? Is it going to offer us a NAT table? Is it going to implement ARP tables? Is it going to implement packet filters or firewalls? There was a day when I feel Windows didn't have a firewall built in, or it didn't really work. But now, you've got a fair number of settings that you can build into that, and Linux has got that as well. They've got firewalls. So you have to ask yourself, okay, do I have networking, and at what level am I going to support it? And then kind of sitting on top of this, you've got to think about the user interface to the operating system. So once you've got the kernel, you've got to figure out how do the users actually interact with this. So am I going to provide them a desktop user interface like Windows or anything like that? And if I do, is it actually a part of the kernel, or is it is it a user program, but you don't get a choice? Or are you going to take a Linux approach where the desktop is something you can add on and you can add whatever when you want? And you can even add as many as you want, such that each day you choose your window manager and you can use a different one. There are so many out there. I'm sure you could probably spend an entire month using a different desktop UI each day. Some of them are really bad though. And if you're not going to support things like that, like a desktop UI, are you going to have shells? Are you going to have terminal support? Are you going to have some kind of command line interface? Is this an operating system built on top of DOS? In which case, we're going to want our users to be able to actually type some DOS commands. And then if you are going to build one of these kinds of UIs, how are you going to handle performance issues? Because if you look at some of the older hardware that actually ran desktop UIs, they actually had to make a lot of considerations about breaking that privilege barrier to make sure that the performance was actually okay for the user. This is really only even scratching the surface. But I hope it's kind of given you a taste of just how crazy it is to design a brand new operating system. And I mean, if you decide to go on and take trains, which is real time, I don't know what number it is, you're going to be building a real-time OS there. But it's a simple one. You don't have a lot of design decisions. I mean, I did not take that course, but my understanding is you've got to write an OS to control some trains. So you got like 2 trains, and that's like all you got to support. And it's a very specific architecture and a very specific system, and you've got like very specific numbers of users, and that's all known in advance. So designing that OS, most of these questions will already be answered for you. So take that into consideration. I mean, if you're interested in OS, I mean, take trains. I've heard it's a lot of work. The last thing to consider is what utilities are you going to offer. Now, this doesn't necessarily have to be a part of the kernel. This is sitting above the kernel. So what kinds of things are you offering to your user programs? So this is what is the kernel's application binary interface. What kind of programming libraries will you provide to your users? Or are they built in or not? Does the user have to go out and get them? Because I know when I wanted to start doing development on my Mac, I actually had to go and get the dang libraries, the development libraries. Some operating systems, on the other hand, provide them by default. Then you have to ask yourself things like system monitors. Do I want to provide my users any kind of system monitoring? Now, that's actually kind of useful because you want to be able to check for runaway programs. How do you present that to people? You want to be able to monitor temperatures. Maybe you don't want to monitor temperatures, but I definitely do. My big render machine, I have like something like 32 cores, and I want to know what the temperature of each of those cores is. And I want to know what the temperature of the graphics card is. And I want to know the speeds of the fans, and I want to know the voltages. So system monitors are going to be actually using system calls to access information about the hardware. So if you're going to offer some of these utilities, you're going to have to build appropriate system calls into your operating system in addition to providing a high-level library or program to do it. And the same with task managers. A task manager is going to give you a list of all the processes and how many threads and how much CPU time they have. And in order for you to offer a user program that looks at the tasks that are running, you have to have system calls built in order to be able to access the information in the kernel. And then there's things like packet sniffers. That's a real fun one. So there are some tools you might want for sniffing all the different packets that are arriving at your computer, not necessarily the ones that are for particular applications, but maybe you just want to see what are all of the packets that my network interface is technically receiving. Because maybe you want to steal some information, or maybe you want to know why your network's running so slow. Packet sniffers can be useful. You also have to consider things like device configuration tools. What level of that are you going to provide in the user side? So there's lots of utilities to consider. And then one of the biggest ones that everybody forgets about is documentation and support. That is a very important thing. One of the nice things about OS 161 is that it's very well documented. Very, very well documented. What we used before this was not nearly as well documented. And the OS I'm hoping to move us to is also very well documented. But if we were to just choose some random OS out there, maybe it's not well documented. And that would make this course and using that OS very difficult. All right. So this is technically the OS of the day. And I've saved it till now because this operating system, if you've heard of it, has made some very peculiar choices in its design that are worth discussing. So, I can see some people on Twitch here are quite amused by this. Temple OS is an interesting story. So this is an operating system that came to be in 2013. It's fairly recent. This is an open sourced operating system. I think it's sitting at about 120,000 lines of code. It's not too bad. You can download the code, you can flip through it, do whatever you want with it. And it was created by someone by the name of Terry Davis, who passed away a year or two ago. I think he was hit by a train. It's a long story. So this is an interesting story of an OS. So first off, if you haven't heard of Temple OS and its creator, the creator, Terry Davis, unfortunately suffered from manic depression and a number of other mental health issues. And my understanding is that he was in and out of institutions, but he was a very brilliant individual, very smart, very good programmer. And he at one point was supposedly an atheist, and then I think during one of his hospitalizations, that just a switch flipped, and he became very, very religious. And the story goes, and I'll let you read it on Wikipedia if you want, or on the webpage, or one of many YouTube videos about Temple OS. The story is that he believed that God asked him to create an operating system that would be God's temple. And apparently, many of the decisions were hence dictated by God. I'm not going to argue about the creation of this operating system. It's very interesting, let's just say that. So this is a biblically themed operating system called Temple OS. And yes, this is the logo for it. So let's look at Temple OS. So first off, it's this weird conflict I have about it, because it supports some very modern concepts and throws some very modern concepts completely out the door. So first off, Temple OS supports multi-core processors. However, it does not support preemptive multitasking. So that is, there is no preemptive concurrency, no time sharing. It only supports cooperative concurrency, which, if you remember, in order for you to have a context switch, you would have to actually have the user program called yield or block or terminate in order to share the CPU. This I don't really feel is that unusual, because many operating systems that we use today have either used that in the recent past or are still using it to some degree. For example, Windows and Mac OS both used cooperative concurrency up until like the late 90s, early 2000s. And iOS, I'm not quite certain if they are still using cooperative concurrency or not, but they were at one point. So this isn't terribly unusual. And if you look at the other features of this particular program, like the user interface, you would realize that cooperative concurrency probably makes sense, because you're not going to have a Chrome window open with 300 tabs, because Temple OS doesn't support networking. It also has a 640 by 480 screen resolution, so having multiple programs open at the same time just doesn't make much sense. There's no screen space for it. Now, let's get into some of the interesting discussion. Everything runs in what's known as ring 0. So we never talked about privilege in terms of rings, but they are usually referred to as rings. So ring 0 is kernel privilege, and ring 3 is going to be user. And most systems are only using 0 and 3. Devices can operate in 1 and 2. If you've got VMs, they'll use more of these rings, but not every OS has used all of these rings. In Temple OS, everything runs with kernel privilege. So everything runs in everything runs in ring 0. That means that the kernel runs in ring 0, but so do the device drivers and the user programs, which has some interesting consequences, as you can imagine. You have no need for system calls, because you can just call kernel code directly. User programs have access to the kernel's data structures and the kernel's functions. Because there's no separation of kernel from user land. And there's multiple ways in which that is true, as we'll see in a minute. So no system calls. And since there's no system calls, and since everything runs in the same privilege mode, threads don't need multiple stacks. They only need a single stack. It also means, since you have no system calls, that it's easier to implement. This operating system has interesting design decisions that have actually shown if you don't take all these security things into consideration, OSs aren't that bad to implement. So without system calls, you don't have to implement, exception handlers that handle the system calls that handle this. But also, if you think about all of the different stack frames that go onto our stacks as a result of a system call, this OS has none of it. None. So if I want to fork a new process in Temple OS, it's faster than doing it in Linux because I don't have to make a system call. I just call fork and it calls the kernel's fork immediately, like directly. I don't need to call get PID. I can just access my own process structure's PID. It's great, right? Of course, so there are positive consequences of doing this. There's negative consequences as well. There's no protection or security. Now, why did he decide to make this decision? I don't know. And you could go down a very deep, dark rabbit hole and try to understand why Terry Davis made this particular decision, but I would warn you against doing so. He offends pretty much everybody. He was not a politically correct individual. I was trying to find the most polite way of putting it. He believed that there was no reason to separate because why would anybody break into God's temple? I think he might have been the only person using the OS. He wasn't worried about security, but if you don't separate the kernel from the user program, then the kernel is going to be able to modify the kernel, and the user program is going to be able to modify the devices in ways that maybe we don't want it to happen. Another very interesting thing about Temple OS is that even though it does support multiple processes and such, there's only one address space. One singular address space shared by everybody. So all programs and the kernel share a single address space. There is no isolation here. This makes things interesting. You can imagine there's a lot of interesting consequences as a result of doing this. For example, if there's no isolation between the processes and the kernel's address spaces, then management might be quite difficult. We might end up with fragmentation issues. We also are letting user programs interact with other user programs. So instead of having to do IPC to send data from one process to another, I can just have my process directly write to their memory. And vice versa. And we can synchronize it even because it's one address space. So I can put a global shared lock and just have both processes use it. So there's some interesting consequences. There's also a lot of negativity to it. And another thing about Temple OS, no real virtual memory. So the architecture, it does use a 64-bit architecture. It's meant to run on Intel CPUs. So they have a paged MMU. I think it uses a 4-level paging system. So Temple OS was required to do that, to support the paged MMU, but he didn't want to use virtual addresses. He didn't want to hide anything. So his virtual addresses are identity mapped, which means that a virtual page X is actually physical frame X. So every virtual address is actually the physical address. So if you make this decision, you don't technically need page tables. I mean, because you can compute on the fly what the addresses are. Because if you get an MMU exception saying this is a TLB miss, all you have to do in VM fault is simply say, oh, I'm just going to put that right back in the cache as the fault address is now the page table entry in the TLP. So, I mean, you don't technically need page tables, which is kind of an interesting consequence. But again, no isolation from processes from each other. And each program can find every other program's data. There's no hiding here. No networking, as I said. None. Nada. Why would you need to talk to anybody else anyways? Temple OS had a built-in oracle which lets you talk to God. So if you can talk to God, why do you need to talk to anybody else? At least that's the story. I don't know how much truth there actually is to that. Scheduling, he decided to use round-robin scheduling, so actually the same as what OS 161 uses. However, remember there's more to scheduling than just choosing the scheduler. If you're supporting multiple cores, which Temple OS actually does, you have to decide how do you support the scheduling for a multi-core system. So are you going to use a shared ready queue or a per-core ready queue? And Temple OS uses a per-core ready queue, which is a very modern idea. And then he had an 8-bit graphical display, so it was 640 by 480. It used only 16 colors, so it reminds me of my childhood. It even had a built-in audio voice. And it supports multiple file systems, so it supports FAT32, ISO 9660, which I'm not familiar with, and he decided to actually build his own file system. And I made the mistake of reading some of his Reddit posts about it, and oh, that was a headache. Don't go down that rabbit hole. His own file system is called Red Sea, because you part the Red Sea. And it's based on chaining, or what's known as blockchain. But he decided that he doesn't want his operating system to become commercial and wanted to really restrict how people used it. So he decided that he wasn't going to allow files to grow. So instead, this would be using an external chain. Instead of using an external chain, he uses a allocation bitmap. So the bitmap is going to indicate that you have a maximum of X blocks, and once you run out of those X blocks, your file cannot grow beyond that. So this is a very simple file system to implement, which if you want to learn how to implement an interesting file system, go look at this. But it's also incredibly destructive. And it was by design. That's the way he wanted it. So what's interesting about this operating system is the design decisions have had a significant impact on the implementation. It is vastly different from any modern operating system that you see today. And because it's open source, you can download the code to this and you can take a look at it. You want to know what it's like in an operating system when there's no separation between kernel and user programs? Take a look. It's not a code. I was actually flipping through the code for the last few days, and it's very easy to understand. The concepts that are used, very easy to understand. The implementation is easy to understand. So do take a look if you're interested. Now, one quirk. So Temple OS was written in a different language. It was written in what's known as Holy C. And Holy C is his own variant of C that has a number of changes. So there's no main function. Everything at top level will be executed upon compilation. So this is like a JIT compiled language, means just in time. So as you compile, that's when you run. When you're running, you are compiling. That's kind of cool because that's actually a really neat performance thing. No main. There are classes in this version of C, and there is support for reflection. And what's interesting about the compiler is that the symbol table is actually accessible globally during runtime. So you don't actually need things like environment variables in Temple OS because any program can just access the program symbol table and grab the value from it. So there's no need to have environment variables because we have access to all the symbol tables. So Holy C in itself is another thing that's interesting about Temple OS. And if you're wondering what it looks like, there you go. And down here at the bottom, you can see it's telling you information about what it's doing. And then you've got, it looks like it's connected to a FAT style file system right now because we've got the 2-part file names. And then you've got some of his applications, which you can see a lot of it is biblically themed. But there's things like something for a budget. He likes guns, apparently. And so he's got these different programs. And you could download this and you can play with it if you want. And no, Temple OS is not going to be CS350's new operating system. I'm sorry if that disappoints you, but to be honest, it's just too offensive. too much of the documentation is offensive and it's too off. If you want to learn about this on your own, by all means, go ahead. I would recommend against watching the YouTube videos of Terry Davis online because they're very offensive. But I'll leave it at that. All right, so this is, as of this moment, officially the end of CS350 Online, now that you've got your full 24 episodes. So I hope that you have a good remainder of the term. If you're working on A3, make sure you note the deadline extension that's been posted to Piazza. The other thing is, don't forget you will have a final assessment that will be offered through Learn, and that is going to be just like the quizzes and format, so it'll be automatically graded. There will be more multiple choice and calculation problems than the regular quizzes, but you get 3 attempts. All right, so have a good rest of the term, and I hope you have a good co-op or whatever you end up doing next term. I hope things work out well for you. See you next time. Maureen, come on. Come on. It's okay. It's all right. Okay, come right here. Okay, what are you going to say? Bye-bye. Bye-bye. And don't forget to subscribe. Okay, no. Face this way. Face this way. Look at the camera. Look at the camera, boys and girls.
Bye, guys. Don't forget to subscribe to our channel. Bye. Bye. So
There you go. You just need 1 more minute.
What's
for
that?
This video to play. Good job. Good job. Dragon? No, that's Maury's necklace.